I will start presenting my lecture. Thank you, Professor Ganguly and Arindam and Calcutta Mathematical Society for asking me to come and interact digitally with you all. I can see there are about 202 participants already in the...
there are 1,500, Professor Rana, 1,500 participants. Rest are in YouTube. Right.
Others are following. On the Google Meet, there are 201 already. So, and many of them will be students. So it will be nice to interact with all of them on this platform. So I will start presenting my slide, and I will request all of you to please do not present anything from your side, and please keep your mic mute, and possibly your phone also, because otherwise it may cause some problem. So let me start my lecture. Can you see my screen?
Yes, sir.
Yes.
So
yes, sir.
My voice also is okay?
Yes, sir.
Yes, sir.
Okay. Yeah. So I am starting my presentation. Will somebody keep track on the chat box, because I am going to ask questions, and the responses somebody can read and tell me the response, because I can't see my presentation and the chat box together at the same time. So somebody will be doing that?
Yes, sir. Yes, sir. I am taking care of this one.
Okay. Who is it? Please tell me your name so that I can call you. Hello.
Hello. Yeah, myself, Dr. Kaushik Ghosh, and I am taking care of the chat box.
Okay. So, Mr. Ghosh, I will be referring to you again and again. So, I am starting with a question which answer to that. Please try to put in your chat box. What is this you see on the screen? So, quickly write something in your chat box so that Professor Ghosh can respond back and I can go ahead. I give you 1 minute to write what this thing you see on the screen.
So everybody is writing pi.
Pi, very good. So you know what should be my next question? If everybody is writing pi, my next question is what is pi? What is pi? Can you write quickly one line in your chat box? What is pi? And Professor Ghosh will do the honor of telling me some responses in the chat box.
Ratio of circumference and diameter. Someone is writing, and also international symbol, irrational number. These things are also coming out. Okay. So let me just take these three responses. One of them says it is a ratio of the circumference to the diameter. That is one response. Somebody said it is an irrational number. That doesn't answer the question, what is pi, right? It only tells the property of pi. So as a student, you should know what is the question and what is being asked so that you can answer properly. So the answer given by one of the participants, which is the textbook answer, is the following. So this is a possible answer which is given in NCERT Standard 8 Mathematics book, Chapter 11, page 219. And it says, if you read at the bottom, it says that the ratio of the circumference to the diameter is a constant. It is a constant and is denoted by pi. It is approximately equal to 22 by 7 or 3.14. Now the question comes, the NCERT books gives you 6 examples of some circular objects and asks you to find out what is the diameter, and so it is a statistical way of saying that the ratio comes out approximately 3.14. And
From this statistical thing, you generalize and say that the ratio is always a constant. But is that a theorem? If this is a theorem, where is the proof of this theorem? I'm sure none of the students or even some of the others would have ever bothered to question where is a proof of the fact that the circumference divided by the diameter is a constant, and that constant we call it as pi. Almost everybody takes it for granted because somebody in the Greek mathematics stated this, okay, and actually gave some kind of a proof which was not very rigorous. So this is my starting point, that what is pi, which is taken as the ratio of circumference to the diameter. Its definition is not known to any school student. Now I'm saying any, because some of the very, very bright ones might have questioned it and tried to read a proof somewhere. But even with the help of Google, you may not be able to find a place where you can find a proof of that. Hopefully by the end of this lecture, I will come back to this question again. So let me start with this is our symbol pi. If you try to write it in terms of decimals, it is 3.145926 and so on. It goes on. It never repeats. It never terminates. And that is what we call it as an irrational number. That is one way of characterizing real numbers which are irrational. We call them as irrational number. And here is a nice quote. It says, I am proud to be irrational. This number is a very important number. Without this, many things, if we don't know, it's an irrational number, we cannot compute it exactly. But if we can find a good approximation to it, that is what is required to do many applications of it. So we'll come back to it probably later. So let us start with the beginning of my presentation, what is called, So this is my presentation, and if you see on the screen, you are probably, I missed something, so let me, some of the mathematicians who have contributed in the journey from numbers to analysis, they are being displayed here, and you'll find some of the Indian names appearing, Brahmagupta and Mahavira and others coming. This is just to Richard Dedekind and George Cantor were two of the important mathematicians who contributed to this real numbers. Isaac Newton and Leibniz, Peano. These are all mathematicians who have contributed in evolving from numbers to analysis. Weierstrass gave example of a everywhere continuous but nowhere differentiable function. Cauchy is very important in the rigor of analysis. And Riemann, we all are famous. We are all know Riemann integration, but many other contributions. Cantor is called the mathematician who knew infinity. Wallis is more known for physics, but he is the one who gave representation of number system as line. So let me go over to starting with numbers. The question is counting and measuring are integral parts of our day-to-day life. We count and measure. Examples are measuring the height of a person. We start measuring our height in our childhood. Our parents do that. And then finding what is the volume amount of some liquid in a container, how much milk is there in that pot, and so on. And then counting money, very important thing. The whole world revolves around money, and we count money, how much money we have got. But have you ever wondered what is the aim of this measurement? what is the aim of this measurement, any kind of measurement? What is the objective of this? The main objective is that we want to assign some numerical value to an attribute or a characteristic or a property of the object. That is what measurement is essentially about. For this, counting numbers are important. So the natural numbers, these are the symbols for natural numbers from around 1000 before Christ and evolving into. So let me probably show you a small clip which will be nice.
Numbers have been a fact of life throughout recorded history. Early humans likely counted animals in a flock or members in a tribe using body parts or tally marks. But as the complexity of life increased, along with the number of things to count, these methods were no longer sufficient. So, as they developed, different civilizations came up with ways of recording higher numbers. Many of these systems, like Greek, Hebrew, and Egyptian numerals, were just extensions of tally marks, with new symbols added to represent larger magnitudes of value. Each symbol was repeated as many times as necessary, and all were added together. Roman numerals added another twist. If a numeral appeared before one with a higher value, it would be subtracted rather than added. But even with this innovation, it was still a cumbersome method for writing large numbers. The way to a more useful and elegant system lay in something called positional notation. Previous number systems needed to draw many symbols repeatedly and invent a new symbol for each larger magnitude. But a positional system could reuse the same symbols, assigning them different values based on their position in the sequence. Several civilizations developed positional notation independently, including the Babylonians, the ancient Chinese, and the Aztecs. By the 8th century, Indian mathematicians had perfected such a system, and over the next several centuries, Arab merchants, scholars, and conquerors began to spread it into Europe. This was a decimal, or base 10 system, which could represent any number using only 10 unique glyphs. The positions of these symbols indicate different powers of 10, starting on the right and increasing as we move left. For example, the number 316 reads as 6 times 10 to the 0th power, plus 1 times 10 to the 1st power, plus 3 times 10 to the 2nd power. A key breakthrough of this system, which was also independently developed by the Mayans, was the number 0. Older positional notation systems that lacked this symbol would leave a blank in its place, making it hard to distinguish between 63 and 603, or 12 and 120. The understanding of 0 as both a value and a placeholder made for reliable and consistent notation. Of course, it's possible to use any 10 symbols to represent the numerals 0 through 9. For a long time, the glyphs varied regionally. Most scholars agree that our current digits evolved from those used in the North African Maghreb region of the Arab Empire. And by the 15th century, what we now know as the Hindu-Arabic numeral system had replaced Roman numerals in everyday life to become the most commonly used number system in the world. So why did the Hindu-Arabic system, along with so many others, use base 10? The most likely answer is the simplest. That also explains why the Aztecs used a base 20, or vigesimal system. But other bases are possible too. Babylonian numerals were sexagesimal, or base 60, and many people think that a base 12, or duodecimal system would be a good idea. Like 60, 12 is a highly composite number that can be divided by 2, 3, 4, and 6, making it much better for representing common fractions. In fact, both systems appear in our everyday lives, from how we measure degrees and time to common measurements like a dozen or a gross. And of course, the base 2, or binary system, is used in all of our digital devices, though programmers also use base 8 and base 16 for more compact notation. So the next time you use a large number, think of the massive quantity captured in just these few symbols, and see if you can come up with a different way to represent it.
Yeah. So this was a brief history about the numerals, their position value, and how Indian mathematicians also contributed in that. So let me go over to the next stage of evolution. So this is the natural number system that we use and is denoted by script n, 1, 2, 3, 4, and so on. And these numbers are used in process of counting. We start counting very early age, even before we go to school. And the process of counting is a process of associating with each object to be counted a unique natural number in a one-to-one manner. That is very important. And to understand what is underlying thing, this process of counting is based on based on a principle. It is a principle which we assume, which is very heuristic or very obvious, and that is called the Pigeonhole Principle. So let me just show you something what is called Pigeonhole Principle.
The Pigeonhole Principle is one of those ideas that sounds completely obvious, but turns out to be pretty useful. Here's the idea. Let's say there are 4 pigeonholes, and let's also say we have 5 pigeons, each of which needs to be put into one of those holes. The Pigeonhole Principle says that after we put each pigeon into a pigeonhole, there must be at least one pigeonhole that has multiple pigeons in it. And that's it. That's the whole idea. Or I suppose to state the principle a little more generally, if we have n pigeons put into n pigeonholes, and n is greater than m, then there must be at least one pigeonhole that contains more than one pigeon.
So this is a Pigeonhole Principle which is very useful in counting. And it, for example, it says mathematically you can think of it as every set has got a unique, either a unique natural number associated with it, or you cannot associate a unique natural number, but you go on counting. So what is a finite set and what is an infinite set? And the finite set has got a unique number of elements in it. This is a consequence of this Pigeonhole Principle. So the Pigeonhole Principle, as the video also said, you can put it mathematically that if there are m pigeons are put in n holes, and m is bigger than n, there must be at least one hole containing more than one pigeon. I am tempted to do an online sort of testing of this Pigeonhole Principle and application of this. Please try to put in your chat box the number. If your date of birth is say 14th of April, just put the number 14 in your chat box. Or whatever is your date of birth, the date of, don't put the month, don't put the year, just the date. Put the date in your chat box and I will claim something, and Professor Ghosh will verify that. So all the participants, if you are able to put something in the chat box, that is the date of your birth, right? So it will be a number between 1 and 31. So 1st of January or 20th of February or such things. Please put one of your number, and Professor Ghosh will verify for me that there are at least 2 participants, 2 persons attending this meet whose date is same. So Professor Ghosh, can you just keep an eye on the chat box? Hello?
Yes, sir. Yes, sir.
As soon as you find at least 2 persons having the same number written, please say I will go ahead.
Yeah, I got 15 perhaps thrice or 4 times. 7 is coming regularly.
Okay, good, great. So thank you. This is the simplest application I can think of the Pigeonhole Principle. See, the number of what I have done is the number of dates is 1 to 31. So there are 31 numerals, and the number of participants I know is positively more than 31. It is, as Professor Ganguly said, on the Google Meet, we have got 200 plus participants and maybe more than 1,000 on following. So positively Pigeonhole Principle will ensure that there are at least two persons having the same date of birth. So let me go ahead. There are many more complicated applications of this Pigeonhole Principle. Nowadays, Google is a very good source to find out what are the possible applications you can see or you can read for Pigeonhole Principle. It's a very simple principle, very simple to understand. It is a principle which we assume. It is not a theorem that we need to prove. It is something that we assume. Intuitively, it is very clear. So let me go ahead. As the civilizations progressed, the trade and commerce progressed, one realized that you cannot solve an equation x plus n is equal to m, where n and m are natural numbers. Find x such that this, because there could be, this n is bigger than m, so you cannot find a solution for this. So this motivated mathematicians to discover what are called negative numbers and arithmetic concerned with that. So Indian mathematician Brahmagupta is credited with the development of arithmetics of natural numbers. By the way, this zero was added much later by the, also it is believed by the Hindu mathematician called Mahavira somewhere in the 19th century. So now these negative numbers started getting familiarity in mathematics. Mathematicians of 15th and 16th century, of 15th and 16th century called negative numbers as absurd numbers. So negative numbers were not that readily accepted by even mathematicians like Rene Descartes, who said that such numbers are false numbers. And then by 19th century, end of 19th century, mathematicians started accepting the need and use of negative numbers and their arithmetic. And finally, it was one of the famous mathematicians, Kronecker, who said, God made integers and the rest is work of men. But even now, we don't, mathematicians nowadays don't believe negative integers is a creation of given by God. Even natural numbers can be created from set theory. So I will not go into that. Let us go ahead a bit. So that gives rise to a set called integers, where every number had a negative counterpart, 1, minus 1, and so on. 0 was added to it. And this gave rise to something called integers, the set of integers. Integers had addition and multiplication defined on it with some properties. So let me skip that. As people developed more and more of commerce and other things, civilizations progressed, the need for fractions came into picture. Civilizations, for example, a man wanted to distribute his property or his whatever. He had 15 cows and 3 children. He wants to give it to all of them and equally. So that came the need for division, and fractions arose. Mathematically, fractions are motivated by the mathematical question of solving the equation P multiplied by X is equal to Q, where P and Q are given natural numbers. This gives rise to fractions where P and Q are integers, but later on it was extended to integers. So finally one came to the definition of the rational numbers or fractions, m by n, where m and n are integers and n is not equal to 0. So this is called a rational number or a fraction. And here I would like to pause and say something about this notation. Here it is m by n, m divided by n, where m and n are integers and n is not equal to 0. I think there is a better way of representing this. This is the one which is given in the textbooks. For example, NCERT textbooks give a rational number as just stated P by Q, where P and Q are integers and Q is not equal to 0. Right? Because division by 0 is not allowed. But I think there is a better way of writing this. We can write rationals as m by n, where numerator m is an integer and denominator n is a natural number. So keep in mind, compare it with the earlier one, where n was allowed to be an integer, but n not equal to 0. There is no need to do that. You can write a rational number as m by n, where m is an integer and n is a natural number. When you say n is a natural number, obviously n cannot be 0, so you don't have to mention that. So this is I think this is a better way of representing rational numbers. Why it is a better way? One, it looks neat and clean. It looks very nice. And the second reason is, suppose you have got a fraction 2 by 3. And if you allow in the denominator negative integers, so look at the fraction 2 by minus 3. In our primary classes, we are told 2 by 3 means you divide into 3 parts, divide something into 3 parts, and 2 parts of that is denoted by 2 by 3. What is meaning of saying dividing 2 into minus 3 parts? That physically doesn't make sense. That does not collaborate with our understanding of fractions. So we can't divide an object into minus 3 parts. That looks a bit odd. So that is one observation, that we should not be putting negative things in the denominator. And the second thing is, supposing we want to do arithmetic of fractions, I want to add 2 by 3 and 1 over minus 1 over 5 in that earlier notation. So if you want to do that, then how do you do? The obvious method, or the method told in the classroom, is this negative sign is pushed up. So you take LCM of 3 and 5 then, and then solve the fraction. So to solve this fraction, you have to push this negative sign up, okay, with minus 1. So it has to be 2 by 3 plus minus 1 by 5. Okay. So these are two reasons I think it's a better way of writing rationals is this thing. Okay. M by n, where instead of saying m and n are integers, we should say it is m by n, where m is an integer and n is a natural number. Okay, think about it. And so let us go back to a history a bit. Around 600 BC, the Greek mathematician led by Pythagoras, Pythagoras and his followers are all called Pythagoras. They all believed everything is a number. And so they believed that they believed in the elementary theory of ratios and proportions, and they believe any two ratios are commensurable. They are multiples of each other. But this belief wanted them to represent points on the line called the number line. This worked very well for some years, probably 100 years. Still, a follower of Pythagoras by the name Hippasus of Metapontum in 500 BC discovered that there are ratios of lengths which are not commensurable. For example, he said that the ratio of the diagonal to the side of a square cannot be commensurable. That is same as saying that algebraically you can reframe this as a question that does there exist a number x, say that x multiplied by x is equal to 2. Obviously we know the answer to this now because we have gone through our school books of standard 9, says this is not true, but this was discovered around 500 BC, and this caused a lot of problem in the Greek mathematics, but this was resolved by doing something, adjusting what is called the proportionality was redefined. But still this question remained that whether this has a equation has a solution or not. This was hushed up by the Pythagorean school. In geometry, this has a solution. However, does the real number x say that x square equal to 2 has no solution as a fraction. So there is no fraction such that x is equal to p by q, say that p by q square is equal to 2. This was discovered around 500 years before Christ by the Greek mathematicians, but was not accepted by the Greek mathematicians. They said, no, there is something wrong with this argument. And what is the proof of this? There is a proof given in the NCERT books. For example, it says square root of 2 is irrational. There is a long way of proving it. I want to give a proof of this, which here is a proof given in NCERT book. So let me just go through. It says a proof is based on the technique called proof by contradiction, which was the first time employed by the Greek mathematicians, which we use even till today. The idea is that if you want to prove something, assume the opposite of that statement. Assume the negative of that statement. And once you assume that, you do some calculations and finally you reach a conclusion which is not possible. So that will mean that with your assumption, your conclusion is not possible. There is a contradiction in your conclusion. So your assumption must be wrong. So what you wanted to prove must be true. So it is an indirect way of proving the proof by contradiction. Right. So the proof is as follows. It says that assume there is a fraction m by n whose square is equal to 2. So when you cross multiply, you will get m square is equal to 2n square. Now m square equal to 2n square, right hand side there is a multiple of 2 that says that m square must be an even number. And here is what NCERT book goes a bit sloppy. It used to be, I think they have amended it a bit now, that if m square is even, then m must be even. A proof of that was not included in earlier NCERT books. Now they have given some arguments for that. They have tried to amend this, but still the proof is not very good. So it says m square even implies m is even. So here m square is even, so implies m is even. If m is even, it must be a multiple of 2. So let us say m is equal to 2k. If m is equal to 2k, put the value in this equation. So you get 2k square is equal to 2n square. And when you open out the bracket, it gets 2k square is equal to n square. And that again implies now that n square is even. So this equation implies n square is even, and hence n must be even. Right? So n is even, m is even, so m and n both are even, so they must have a factor in common. But to start with, we could have cancelled those factors and we would have gotten a contradiction. So this is the proof, but the lacuna in the proof is that this assumption. So let me show you how this assumption can be overlooked, need not be used. So let me go over to a proof. I got 4 different proofs. So let us come back to the proof by contradiction again. Suppose m by n square is equal to 2. So assumption that there is a fraction m by n whose square is equal to 2. So when you cross multiply, you will get that m square is equal to n square. M square is equal to 2n square. Now here m square is divisible by n square. That means what? That means m and n must have common factors, right? So you'll say that that is again a something which I don't believe, because that also needs a proof. Okay, so let me give you a proof which is much simpler, and let us look at this. Look at the equation m square is equal to 2n square, right? Now look at here, if I look at this equation, look at the number 2. The number 2 is a prime and it occurs in the prime factorization of 2n square. So keep in mind, 2 is a prime and m square is equal to 2n square. That means 2 appears in the prime factorization of the square of a number m square. But if 2 occurs in the prime factorization of 2n square, right, then it will occur in odd number of times, because in n square, in the prime factorization of n square, 2 can occur at the most in prime number, in even number of times, because 2 may occur in the prime factorization of n, and in n square it will double it. So in the prime factorization of n square, 2 will appear even number of times, and 2 is already sitting here. So if I look at the right hand side, the prime 2 appears odd number of times in the prime factorization of 2n square. But if you look at the left hand side, the prime 2 may or may not appear in the prime factorization of m square, but if it appears, it must appear in even number of times because it is a square. So that is what gives a contradiction, that m by n square cannot be equal to 2. So, the advantage of this proof is I can replace 2 by 3, I can replace 2 by 4, 2 by 5, 2 by 7, and the same proof works. So the same proof works and shows that there is no rational number whose square is equal to a prime. So this proof can be generalized. This is what I have written here, that the proof can be generalized. It can be generalized to cubic equations also. So that is what mathematicians do. They will look for arguments which can be extended and generalized. So I have given you a proof of the fact that there is no rational number whose square is equal to 2, and that proof can be generalized. So the discovery of this kind of numbers like square roots started appearing in the mathematics literature. Though Pythagoreans had ignored it, but they started appearing. Their use was necessitated by applications and so on, and they gradually irrational. People started calling such things as irrational numbers, and they gained importance. It was only in 1872 that the mathematician Richard Dedekind and George Cantor precisely defined what are real numbers. Both gave precise definition of real numbers. They started with the notion of fractions, that there are fractions, there is arithmetic of fractions known, but in the set of fractions, equations like x square equal to 2 cannot be solved. So they wanted to enlarge this class of real numbers to a class of rational numbers to a bigger class, and they did that, and they call it as real numbers. So this construction is not that easy. That's why it's not done in school level, and it is not also done unfortunately done in college level also. The construction of real numbers from rational numbers, I think some of the universities are doing it in their BSc courses, but many of the universities have removed from their syllabus in an effort to upgrade their syllabus, which I think is not a very good idea. So this construction was done by Richard Dedekind, and then independently by George Cantor. The two mathematicians separately did that, and the approaches of both of them are categorically different. They are different from each other. One looked at the geometric property. Richard Dedekind looked at the geometric property of real numbers as a line segment and introduced the notion of what is called a cut. And George Cantor looked at what is called sequences of rational numbers and their limits. So both are slightly advanced topics which you will come across in your higher mathematics if you do that. So the construction of real numbers from rational numbers is not as that straightforward a job. It requires a lot of work, right? And if you want to read more about this, probably you should read my book titled as From Numbers to Analysis. The book is called From Numbers to Analysis. The book is published by Word Scientific, and it gives a lot of historical perspective and a lot of analysis in that. So if you can get hold of a copy, do go through it. So let us go ahead a bit the Pythagorean school believed that everything is a number, right? So, and that numbers must be representable on the number line. But they found that the length equivalent to the diagonal of a triangle, of a square of length 1, that point is not representable as a rational. So that means rationals, when put on the horizontal line, do not occupy every position. There are gaps left out. And these are precisely the gaps which were filled by Dedekind and George Cantor. And once that was done, it was John Wallis who said that the real number system, the set of real numbers, is in one-to-one correspondence with points on the horizontal line. So he made the Pythagorean dream of representing numbers with geometry, relating with geometry. So that was a very satisfying thing. Everything seemed complete. So let me say George Cantor and Richard Dedekind realized mathematically the real numbers as a ordered field which is similar to that of Q. Q is also an ordered field. What does an ordered field mean? Is a mathematical term. You can add numbers, you can multiply numbers. Under addition, it forms, for every number there is a negative number, it forms a abelian group. I'm using some mathematical terminology. And under multiplication, non-zero numbers form a multiplicative group, which is also abelian. And the two, addition and multiplication, interact as the distributive property. So both are ordered fields, and rationals are inside R. They are a subfield of rationals, but the rationals lack a very important property, what is called the completeness property, which real numbers have. So what are the completeness property of real numbers? It says every monotonically increasing sequence of real numbers that is bounded above is convergent. All this what is a sequence of real numbers, what is monotonically increasing, what is convergent. They are all terminologies from the higher order mathematics, like first year of BSc. You will come across these things. Rational number do not have this property. That means there are monotonically increasing sequences of rational numbers which are bounded above, but they do not converge to a rational number. But this property this shortcoming is removed by enlarging Q to a bit bigger field called R of real numbers, in which every monotonically increasing sequence of real numbers is bounded above and is convergent. So this property of real numbers, one of the consequences of this real numbers is that you can precisely define what is that number pi. So let me probably show you something which students should find it very interesting and appealing. I would like to introduce a software called Geogebra, and I would like to show something in Geogebra. So here is a applet made in Geogebra. Okay. So what is Geogebra? I will just probably tell you that. But so here is, if you like, you can look at the top. Doesn't say anything. Okay. So let me probably say something about Geogebra, because many of you may not be knowing what is a Geogebra. Okay. So let me go to Google, if I can do it. No, I cannot do that because I have to leave my presentation. Okay. Right. So let me probably continue. Let me probably in the help about license. Okay. So So here is, okay, I think this is good enough to show. Here is if you can see on the screen, there is something called Geogebra Classic. And there is a number written to it, right? This is a software which is available on the website called www.geogebra. Geogebra is the combination of the first three letters of geometry. So geometry, G-E-O, geo, and last four letters of 5 letters of algebra, so forget EL and Gebra. So the two are combined together to give you a software called Geogebra. And this was a software which was developed by a PhD student of computer science in Austria. And this is a open source, freely available software. You can go to that site, which I just now said, www.geogebra.org. From there, you can download and use it very easily. You can learn very easily what is that software. And it's a very useful thing and doing many things. So I think you should start exploring the software called Geogebra. It does not cost you anything. It is free. And there are many things made in Geogebra and available. So let me show you something which has been done in Geogebra. And that is the following. So let us try to, the problem is to find the area of the unit circle. So this is a circle of radius 1. Okay. This is a circle of radius 1. I want to find out what is the area of this. And I know my mathematics says that the area of the circle of radius 1 is pi r square, r is equal to 1. So the area is equal to pi. And pi is an irrational number. So you cannot find exact value of this irrational number pi. But this was done by Archimedes. He said you cannot, he didn't say that you cannot exactly find because he did not know the word irrational. It was proved much later on by that pi is an irrational number. But you can find a rational approximation to it. So you can find a value of pi, a value of this area of the unit circle, which is very close to the area of the circle. And the idea is very intuitive. What you do is you try to inscribe a triangle, a equilateral triangle inside it, and you find its area. That we can find because we know what is the radius of this is one particular distance, and you can calculate half base into height. So what we are going to do is we are going to increase the number of inscribed n-gons. If I make this n to 4, so you see more area inside the thing is captured, inside the unit circle is captured by the square compared to what was in the triangle. So more area is covered. So if you can find the area of this square, that will give me a better approximation to area of the circle. So now the method that Archimedes employed is the following. He kept on increasing the number of inscribed n-gons inside the unit circle. Right? And if you want to, okay, so let us see what the software says. Say n is equal to 4. Yeah, so n is equal to 4. So it says A4 is equal. So here you can see if the radius is 2, the area of the 4-sided n-gon is equal to 2. So let me increase the number of sides and keep an eye on this A4, A5. So this is A9. A9, the area of the 9-sided n-gon inscribed in the unit circle is 2.893. So as I keep on increasing, my approximation becomes better and better. After some stage, you can't see because the n-gon almost looks like a circle, but you see that it's already approaching that required value, that value that we think of, the 3 decimal places. In A146, this is the value, right? I can go up to 200 places, the value stays, right? Probably I can change options, rounding. Instead of 2, let me put it 10 places and see if I can get something better. No, I think my result does not show a better thing. So this is the way it was done by Euclid. He did it, of course, very heuristically on paper and pencil. We can do it in a software called Geogebra. So let me just, so this is, what's the aim of this? The aim of my showing you this was that as the number of sides increase, AN, the area of n-sided n-gon is increasing. So this is giving a monotonically increasing sequence of the areas, and eventually it should become the area of the circle. And this sequence of numbers ANs are bounded above. They are bounded above by the area of the square in which the circle lies. You can draw a square, and you can draw, for example, I can just draw a simple square, a regular polygon. For example, if I take this and take it four-sided, and I can move this, and I move it. Yeah. Okay. Now you see that the area of the circle is always less than or equal to area of all n-gons is less than or equal to the area of the square. So this is a monotonically increasing sequence which is bounded above. So this is a monotonically increasing sequence which is bounded above by the number which is the area of the square. So it must converge. So it will converge to a number which we can define to be the area of the unit circle, right? So this is the most precise way of defining the area of the unit circle by Archimedes' method. So this is the Archimedes' method which gave the area of the unit circle. This is the beginning of the topic analysis. We have only come to the stage where real numbers are defined properly, and then analysis of real numbers, properties of real numbers, and then the properties of functions of real numbers. They all are part of the study of real analysis. It's topic for studies of higher mathematics. So I think I will stop here my presentation and probably give more time for the question answers. Versa Ghosh?
Thank you, sir.
Yeah.
Now, Kaushik, is there any feedback on question answers, please?
Yes, sir.
Go ahead.
Yes, sir. Some questions are there. Let me just say one by one. There is one question that has been asked that from the very definition of rational number, whether 2 by 4 and half are different or not?
Right. That's a very good question which comes across in school mathematics. Is 1 by 2 same as 2 by 4? Right? You can say 1 by 4 is the smallest way, is the, what is it, school level, they call it, I think they call it a standard representation of a rational number. Because rational number, actually I'm not, from when you construct from integers to rational numbers, you construct as a set of numbers. For example, 1 by 2 is said to be equivalent to 2 by 4. So when we do arithmetic, we don't differentiate between 1 by 2 and 2 by 4. We treat them as the same rational number. Okay? Yeah. There are different way of representing the same rational numbers. You can take it that way. Next question.
Yes, sir. One question is there, why pi has been approximated as 22 by 7?
Yes, it's a very good question, and that leads a lot of confusion for school teachers as well as students, that why pi is taken as 22 by 7. Because when Archimedes, I said you can approximate it by the inner polygon of n sides. Archimedes, when he did it for n equal to 3, he got that pi is less than 22 by, is bigger than 22 by 7, but less than something, which is slightly bigger than 22 by 7. So it is a third stage approximation for pi, and for school level is a sort of a good approximation taken, right? You can have a slightly more bigger approximations as fractions also if you need, but that will complicate only computations. But it should be mentioned in the classroom and in the books that pi is not equal to 22 by 7, pi is approximately equal to 22 by 7. It is only an approximate value. And it was the one which was suggested by Archimedes up to third stage of approximation. Yeah.
Yes, sir. Next question is, can we find the area of a triangle inscribed in a circle using Cartesian system? That's
you can. Why not? You can use your geometry if you want. You can take the circle to be centered at origin, and then you'll have a triangle which is a equilateral triangle, and you will know what is the altitude of that triangle. This is not a difficult half base into height. You will know what is the base. Base is the right. What is the base which is in the triangle, which is in the circle, and what is the height? Half base into height. That is not a difficult thing to find using coordinate geometry, if you like. Yeah, and that's how actually Archimedes did that basically. Yeah.
One more question is there. That from real number system, the extension is complex number system. Is there any further extension of this complex number system?
See, we don't extend number just for the fun of it. Because integers were extended to rational numbers because some algebraic equations could not be solved in integers. We extended rational numbers to real numbers because some other equations like x square equal to 2 could not be solved. But everything was okay, right? It could be done. But there were equations like x square is equal to x square plus 1 is equal to 0. Such algebraic equations cannot be solved in the real number system because x square plus 1 equal to 0 will give you x square equal to minus 1. So you have to construct a field, you have to construct a bigger field called the field of complex numbers. But where these algebraic properties are viable, where equations like x square plus 1 is equal to 0 is solvable. So algebraically such equations become solvable, but you lose something. That field of complex numbers, though it includes real numbers, is not complete, is not order complete, is not sequential complete. You cannot say there is a sequence, every sequence of complex number which is monotonically increasing will converge. Because the reason is you can order real numbers, but you cannot order complex numbers. Given two complex numbers A and B, Z1 or Z2, you cannot say Z1 is bigger than Z2 or Z1 is smaller than Z2 or Z1 is equal to Z2. Which property is true for real numbers? The law of trichotomy is true for real numbers, which is not true for complex numbers. So extensions of number systems are done with the requirements in mind, okay? Not just for the sake of it.
Right. Thank you. Next question is, why then pi has 180 angle measurement in geometry?
What is it? Not clear to me.
Why pi has 180 angle measurement in geometry?
Why pi has angle measurement?
180 degree angle measurement in geometry.
Why pi has taken 180 degrees? I have not taken 180 anywhere.
Yes, of course. Yeah, the question is not properly mentioned. Let me come to the next question.
Let me just complete.
There is one question that has been asked in the YouTube chat box, that what is the logic behind the fact there is exactly or just almost 2% participants having the same date of birth?
What is the logic?
Yes.
There is no logic. It is mathematics. It is a logic based on mathematics, and the theorem that the principle I am using is called the Pigeonhole Principle. It is a principle in mathematics which is accepted by our mathematicians. It's a very simple thing. Suppose there are 3 chairs and 4 participants. A musical chair, you can think of a musical chair where at some stage there are 3 chairs and there are 4 participants going around it. As soon as the music stops, there has to be a chair where 2 participants have to sit, if all have to sit. Otherwise, 1 participant has to keep standing. So if the objects number is more than the place where they can put, then at least one of the places should have more than 2 objects put there. So the number of persons attending this meet is much more than 31, and the places 1 to 31 is the dates, number of dates of the month. So you have to put every participant on a date according to his date of birth. Then there has to be at least one, in fact, many, many more who will be sitting at the same place. That means by the Pigeonhole Principle, there will be at least 2 persons having the same date of birth. So that is a logic given by the principle of...
May I add a point here? Hello?
Hello.
May I add a point here?
Yeah, please go ahead.
Because Professor, I heard from the Professor, I am Indian Statistical Institute, but I am not a student of Professor C.R. Rao. I heard from a student that Professor C.R. Rao took his first class and just asking the students their date of birth and predicted that at least 2 students will have the same date of birth.
Yeah, this is a very...
Statistics in ISI.
No, this is the very reason I wanted to bring this exercise here, because this chabis the students very much. You see, because a very simple thing, it has a principle associated with it. For example, an application of this, you go to a bank and you ask for 100 rupee notes, and you're given a bunch of 100 rupee notes pinned together. And the bank counter chap has counted that on the machine. He says they are 100. But when you count it, you feel there are 99 only. But that physical quantity of bundle has got a definite number of numbers, right? Number of notes in it. And that is unique. And so either the bank machine is making a mistake, or you are making a mistake, or both are making a mistake. That is immaterial. But the principle says there is a fixed number of notes in that bundle, right? And probably it should be 100, right? And that unique number associated with that set of notes in a bundle is given by Pigeonhole Principle. Yeah, please, any other question?
Yeah, I think that
Yes,
Dr. Kaushik asked the question why pi is taken to 180 degree. I think the answer of the question is simple. When expressed in radian, that is 180 degrees pi. So it's related to the same thing.
Yeah, no,
Radius of the circle.
To me, I think the problem arises because students have 2 ways of measuring angle. One is in degrees, and the other is in radians. When we are thinking of all calculations about angles in analysis are done with radians, because radian is a real number. Degree is not a number. Okay. Yeah. Please. Thank you.
Yes, sir. There is a question like, is there any particular mathematician who developed the sign of pi or the particular expression of pi? Is there any other mathematician?
Okay, so I think you are now going into the history of mathematics, evolution of the trigonometric ratios. First started with Pythagoras itself, 90-degree angle, and he gave for very simple base angle is 30 and 30, 60, 90 and so on, right? And then it was much later when people realized that if the angle, in the triangle the angle is not 90, can you do something more about it, right? And that I think I am not very sure about the exact history of trigonometry. It's a very good thing to look at who are the persons. Might have been Gauss saying something about it, complex numbers. I am not sure about it. I have not studied complex numbers and trigonometry history very precisely. So I can't answer that question. Thank you. Any next question?
Yes, sir. Last question I want to ask, that someone is asking that, is there any open research field in the area of algebra analysis, etc., geometry?
Any open field?
Research field, yeah.
I don't know whether if I say something, whether the person will be able to understand what is the open research field, right? I would suggest that go to Google. I'll give you a source where there are problems. You can look for the problem posed by David Hilbert in a World National Congress. I forget the year. He mentioned 20 problems which should occupy mathematicians for coming centuries, right? So he has mentioned some of those problems are solved, some are still unsolved. There are many problems called millennium problems, which have a prize associated with it. There is a Fields Medal associated with research in mathematics, discoveries in mathematics. So there are many problems which are important and in analysis. That is what research is. And interesting thing is, in research in mathematics, even if there is no problem, you state a problem. You create a problem and try to solve it. If you are able to solve it, that is good. If you are not able to solve it, you pose it. And if many are not able to solve it, but you have a probable answer, that becomes a conjecture known for you. So there are many conjectures which are solved. For example, Fermat's last theorem was only solved very recently. It remained unsolved for many years. So you can go and look for such things on the Google site. Right.
Yes, sir. The last question is, one is asking, how does anybody come up with the idea of defining pi to the area of a polygon inscribed in a circle of r is equal to 1?
It's very simple. You see, you try to do something which is unknown with known things. So if I understand your question is, how Archimedes could ever think of designing and go and decide it and do that approach. If you want to, for example, give me any, for example, if I take a rectangle and I want to find its area, how would you try to find it? You will try to find what is the length, right? And how do you find the length of and breadth of the rectangle? You will take a unit of measurement. And that unit of measurement, whether be it an inch, be it a meter, be it a mile, you will try to measure the length of that side. You may not be actually able to measure that unit of unit. You may have to shorten that unit. If you have a meter length, your length may be more than 1 meter but less than 2 meters. So you may have to cut out your meter into smaller parts, right? So by known units, you try to measure. For example, for the circular thing, Archimedes realized you can easily find out for the rectilinear figures the area. So he tried to put rectilinear figures inside the unit circle, right triangles, right? Later on, Riemann did it with rectangles. Riemann sums, upper and lower sums, are precisely trying to find out the area below the graph using rectangles. By knowing things, something that you know, that's all. Try to build your thing and logic by knowing things. What you know, you use it to find the unknown. Yeah. Anything else, Dr. Ghosh?
Yeah, nothing significant. I think we should come to the conclusion of this particular session.
Okay.
And let me deliver on the behalf of.
May I comment something?
Yes, sir. Yes,
hello,
sir.
Hello, Professor Rana.
Yes, sir. Please.
May I comment something?
Yeah, please.
Okay. Hello. For the question 2 by 4, 1 by half, 1/2, the same rational number. In addition, if you take the condition P, Q are prime to each other, then this problem is solved. If your definition, if you add the condition P, Q are prime to each other, then this problem is solved. So 2 by 4 and 1 by half is the same number. Next question, the pi is whether I heard that one of the students asked the question, is there anybody dealing with pi? So Euler has done this. There is some conjecture, Euler conjecture. If you take the Euler conjecture, the pi is a transcendental number, it can become up easily. And another is Gerigori series. With the help of Gerigori series, you can evaluate the pi also. So another question is about I am talking the historical development. So if you Dedekind is a part. Previously, they give the existence of irrational number by the geometrical way. Yes. And the Cantor is later on because he introduced the sequence after that. So he was a student of Barrister's. So Dedekind was a friend of Cantor very much, because you know that Cantor was very much shocked by the comment of Pronekar and Poincare when he dealing with the order of infinity. So, but I think that if Dedekind don't come forward, then Cantor cannot lead the mathematics. So after Cantor, Cantor introduced a number of very sequential approach. But these two approaches are equivalent, right? Professor Rana?
Yeah. See, the point is real numbers can be defined as a complete ordered field. It is a field.
Yeah, this is a completeness.
Yeah, there is an order there, and there is a complete. Yeah, so any two complete ordered fields are isomorphic to each other. So Dedekind's method or method of Cantor. Actually, there is a method given by some other people also, by Weierstrass, by interval method also. So all these are equivalent ways of. The idea is to construct rational numbers is a ordered field which is not complete. So complete it by constructing a complete ordered field, and one can prove a theorem. All these are part of are given in that book of mine, From Number to Analysis. That book is published by World Scientific. The only thing is the Indian edition is not available, so I can't recommend it that go and buy it. But go to a library and try to pick up a copy if you can. It gives, starting with axiomatic set theory. You start axiomatic set theory and then go over to fundamental theorem of calculus. See, many people think that fundamental theorem of calculus, that every polynomial of degree n with complex coefficients has got exactly as many roots as real numbers. That is actually a theorem in real analysis. That is a theorem in real analysis. So one can prove it without using any complex integration, contour integration. A completely independent proof given by Arkand is included in that book. So do try to read it as and when you find an opportunity or get hold of a copy. Thank you very much. Thank you everybody for listening to me very patiently. And thank you organizers for putting me in. So, shall I close? Was it good?